Okay. Today we are going to implement about offline reinforcement learning with robots. So last week with the professor we talked about what is reinforcement learning and how we can train offline reinforcement learning. So we are going to train IQL, which is one of offline reinforcement learning algorithm. We first collect the data set with a robot, and then we train the IQL model, and then we test that checkpoint with the robot. So actually the brief pipeline is similar to what we've done in computer vision. So here is our file organization that we are going to use. We have some kind of model structures and parameters that we will have. Briefly, they are in Google Drive, but result and checkpoint or data set is not in Google Drive. You should collect manually. And we have some collect teleoperation data program or play teleoperation data set program. And also run IQL.py, which can run the trained checkpoint with JetRover robot. So briefly in pipeline, in robot, we first going to collect a trajectory using the state and action to grab a cube. When we collect a data set, inside the teleoperation data set directory, the pickle file would be generated. So we are going to use it inside the collab, outside the robot. We using train IQL Jupyter notebook file and IQL directories. We are going to train a policy with IQL, implicit Q learning. And after training, the checkpoint would be generated. Using that, again, we go to robot and use that checkpoint to infer in test time. So to make and play the collect teleoperation dataset, you have to modify some files before. First of all, you have to install this gymnasium library in command, and you have to modify the code in YOLO detector, because in this environment, we are going to use the state, joint state, which is calculated by forwarding kinematics, and also cube position, which is calculated by YOLO detector. So at that time, we only processed the image, which is drawn some rectangles or some axis to see where the position of the cube is. But we are going to add this kind of code to publish with a topic. We are going to publish cube post topic to say the robot about the position of the cube in vector. Next, you are going to design and implement about your state space and the reward, which will be used in training. So the state basically means that what the agent will see in test time. So actually the state can be like some XYZ position or some rotations or the cube's position, because knowing that the agent will execute some proper actions, you can design your state in this empty list with some kind of append functions. And also the reward. Reinforcement learning is basically to collect the largest reward as much as possible. So to make the agent work well, you should design the reward carefully to grab the cube. So you should modify get observation function in manipulation in env_pi, and also the step function in manipulation env_pi. To design, or when you read the code and there are some more codes to modify, you can modify other details to provide the agent with more useful information. And one more thing to modify is inside the kinematics file, which is the residual function that calculates the error. We are going to give rotation weight so that if the weight is 0, then calculating the inverse kinematics, it will not consider about rotation error. So that even if the position of end effector is decided with using only position, it will not consider about its rotation, so it will make more acceptable solution to reach that position. Briefly reviewing about the pipeline, we collect data set using offline data set, offline reinforcement learning. The pipeline is like that. So the robot arm interacts with real world using the camera node and controller node that we implemented using some kind of state and actions. And when some state and actions are acquired, the data set would be processed and then data set would be acquired. To process that data set, we should design some kind of reward, like when if it ends, it adds 1, or if it's not succeed, it gives some -1 scalar or something. So during that data collection, human operator should use teleoperation to record the action. About teleoperation program, we've already implemented in Google Drive, so you may read the code and use it. So to perform task and record trajectories consisting of state, action, reward, and terminated, truncated, and metadata, you should read the kind of GIM interface that is used in reinforcement learning commonly. So go to manipulation experiment directory that you've used in a few weeks, and when you run this collect teleoperation data.py, you can collect data set with teleoperation. Briefly introducing how to teleoperate with those programs. There is some kind of commands that you can type. It is basically WASD and I and U. So if you press W or S, the gripper should move to the positive y-axis or negative y-axis. Or if you press A or D, it will go negative x-axis or positive x-axis. And if you press I or U, the wrist of the gripper should be rotated in clockwise or counterclockwise direction. And if you press space, you can toggle the gripper, R to reset the robot, M to save the current demonstration, and H to print help, and Q to exit the program. You can read the code. And during the teleoperation, it doesn't execute it like after just you pressing W, then it doesn't go up. You should enter. You should press the enter, but you can also press multiple actions at once. Like if you type ASU and then enter, the robot will go left and down, and then rotate counterclock. clockwise. And at that time, the action will be recorded as in one action. So the principle is whenever you record, type these actions, the data set is collected autonomously. And then when you press this M button, you will save those trajectory in one episode to one file, one pickle file. And about IQL, implicit Q learning, because we are going to run this implicit Q learning algorithm, we are going to use one offline reinforcement learning algorithm. So IQL is mainly to decrease some distributional shift with policies, because compared to online reinforcement learning, which uses interaction with real environment, it uses just pre-collected data set from other or experts. So if the data set differs from the real situation that robot faces, it will probably forget about how to execute the proper actions. So in IQL, to prevent overestimation, IQL estimates the upper bound with a expectile concept to predict a Q function. So actually, you don't have to fully know about how these laws are acquired, but to fine-tune or run these hyperparameters, you should know what hyperparameters are used. So to train value functions or Q value functions, this loss is trained by the difference between predicted Q function and ground truth V function. Also, Q function will be calculated using R plus gamma V function minus Q function to using MSE, mean squared error. And to train this policy, we should decrease the loss about exponential of 2 difference times this log probability. So during those functions, we can tune this kind of hyperparameters like gamma or the coefficient that would be added in this loss. So it basically learns a policy implicitly from the Q function without explicitly modeling actions. For each state, this upper bound as the conservative baseline steers the agent toward actions supported by the data and away from out of distribution actions. So IQL's purpose is to keep estimates close to the data distribution, reducing overestimation about value functions. To train this IQL using the dataset we've collected, go to this Google Drive link and copy those files. We don't have to copy and use all of these files because some files are used only inside the robots. Using IQL and train IQL.ip1ip and move some teleoperation data set you've collected in this folder. And inside the Jupyter notebook, after reading some codes, you should execute the kind of cells. And there are some hyperparameters that you can tune, like the temperature that is going to be used in this policy loss, or the max time steps, safe frequency, or the discount vectors that is used. Basically, it will be trained using only these hyperparameters, but you should consider about how many batch size or the epoch to train, because the data set size would be differ from you guys. So train using this code. And after the checkpoint is saved, after the training is over, you can save this actor checkpoint file and then bring it back to the robot. So inside the robot, again, after getting the actor checkpoint file, you should decide this model path and upload, change the path of the file in run-iql.py. After that, you will run this kind of PDF. This kind of functions. If the cube is in front of the robot, it will pick up the cube. And about some tips to collect or train these models. The more variable the data set is, then the more data set is needed. So don't put too much variance when you're collecting the data with small amount of data set. So you should consider to do same or similar actions for same situations so that the agent can get that situation well. And variance of the data makes the model more generalizable, but it needs much more time and data to converge. So even if you are going to execute same actions in same situations, as the state is calculated by some joint and kinematics, it would have some errors or sensor errors or the cube position errors. So the situation is actually different state. So it is enough to execute same actions as well. Train the model at least 500,000 steps. It takes about 2 hours, but it basically will depend on the amount of data set you collect. Collect the data more than 5. And when you read this manipulation in Python file, there is some hard-coded value about gripper threshold, because inside that, if the agent predicts the gripper value, if that value is greater than 0.5, it is coded to just open, and less than 0.5, it is coded to close the gripper or otherwise. If your trained agent predicts the actions about this gripper improperly, you can manually change this gripper threshold value. Like even if the model is trained, the agent outputs only like 0.4, then you can modify this threshold to 0.3 to make this gripper open. So this is what we are going to do this week. And we will check your model performance in a real robot after you send the model checkpoint and then the file you modified. We will evaluate some intermediate behaviors of the robot during the inference, not just whether it succeeds or not. We will check whether it goes down or the gripper is closed, and whether it goes up again, and whether it successfully grabs the cube when we put some cube with some different positions. So basically, if the robot successfully do all of those commands, then it will get 100% point. So you should submit your model path file, that the checkpoint you trained, and the manipulation inf.py that you should modify. And if you modify another course to make it train, then you should send that files also for TAs to run properly in our situation, our settings. You should submit those by email, and the deadline is same as well that we trained for 7 days. And please make the title consistent, not computer vision, reinforcement learning. And that's it. Any questions so far? Okay. If no questions, then we will wrap.